Hello everyone, I am Ahmet Mazacıoğlu, a project analyst at Quick Release. I would like to welcome you to this year's first event of the QR Insightinar series. In this series, we will be capturing bite-sized insights from a diverse mix of experts on a product data management related theme. Today's theme is managing data against shortage, and I have three wonderful panelists for you. Each panelist will present a brief talk, then address the questions from the audience. You can share your questions with us via the Q&A button on the top right corner. And I will be moderating those questions to the panelists after each talk. Without further ado, our first speaker today is our own Helen Crimmins. Helen is a business manager at Quick Release Detroit. She specializes on data analysis and project management to support new product releases for automotive companies. Helen will kick off this event by providing her overview on a highly topical subject, the chip shortage problem on automotive industry. Okay, Helen, what do you have for us today?
All right. So, thank you for the introduction, Ahmet. My name is Helen Crimmins. As you said, I am a business manager with Quick Release, and I'm going to be talking with you today about the chip shortage and how it is affecting the automotive industry. So, to kick things off, here's an overview of kind of what we're going to go through today. So, first, we're going to go through a little background on what we're talking about when we talk about chips and the chip shortage, getting into the difference of sales we saw before the pandemic and as it began starting, the rise of the chip shortage, the impact on the automotive industry, and where we are today. So, first off, going to talk a little bit about chips in general. So, first of all, what is a chip? A chip is a microchip, and in this, we're talking about a series of integrated circuits printed or etched onto a wafer made of a semiconductor material like silicon, and these are produced at a nanoscale. So, by a nanoscale, what we're talking about is imagining that one silicon wafer the size of a fingernail is going to contain hundreds to tens of thousands of integrated circuits. So, because these are produced on such a tiny scale, these require very highly specialized equipment to fabricate these and heavy investments in R&D to keep up with technology. And now, in general, that's what chips are, but zeroing in on the automotive industry, if you take a look at cars, trucks, SUVs, and all the parts that contain microchips, you're looking at 100 or so parts each. Some of the microchips are newer ones that are more complex, so they have more of the circuits printed on them and they can handle more complex functions. Most, however, are older, less complex, and although they do cost a bit less for the automotive companies themselves, they are a lower margin of profit for the chip fabricators themselves. So, taking a look at all these different types of parts that can contain microchips in your vehicles, there's even more that are on this list. And zooming out a little bit, if we look at US automakers in 2019, they sold about 17 million vehicles. So in total, this required billions of chips. So this is what it looked like for the automotive industry itself. So now we're going to take a little bit look at what this looks like across different industries. So despite the large number of components that require chips that go into automobiles, their consumption was actually pretty modest compared to what is consumed by wireless communications, PCs, storage, graphics processing units, etc. Automotive comes in at a very modest $41 billion. And if we take a look to the right, this starts to show the expected growth in each of these sectors from 2019 to 2020. So if you zero in on those black dots, those are our forecasted growth amounts that were made in 2019 before the pandemic took off. Most of these areas were expecting growth of 3 to 10% from where they were in 2019. And automotive itself was expecting around a 7% increase, which was in line with what they had been doing in previous years. Fast forwarding into 2020, the pandemic hit, a lot of changes to the business landscape, and we reach these blue dots here, which show the actual changes in sales from 2019 to 2020. So most of these areas actually saw a much higher growth of 10 to 19% from 2019, as we would kind of expect. Storage, PCs, wireless communications, they gained the most, consumer electronics as well. Industrial applications had no change, and automotive was the only one that saw a loss. Instead of the predicted 7% increase that they were hoping for, they experienced a 9% loss. This huge swing in what was forecasted and what was actually occurred uh, is where we actually begin to see where the chip shortage began to impact these different industries. And now, taking a look at the chip shortage itself, what started it? First and foremost, the chip shortage was driven by digital transformations that were happening across every industry: medical, aerospace, automotive, personal consumer electronics. Everyone was advancing their technology, needing them to be faster, smaller. All of this was driving more and more demand for chips and for more advanced chips. And as this continued, started to outpace the available supply, and when the pandemic hit, it just exacerbated the situation. So when the COVID-19 pandemic hit, we experienced government lockdowns all over the world. Massive groups of people switched from working on site to working and going to school at home. Plants and businesses shut down. There were less people in the workforce. All of these factors caused the already rising demand for PCs, cloud computing, consumer electronics, etc., to suddenly surge. And as you can see from this chart showing lead times, this was captured in 2021. This is what the swing actually looked like in terms of the microchips. We went from different types of chips, depending on their complexity, taking 4 to 8 weeks to get from the fabricator to the next step in the supply chain where it's installed into a part, to going up as high as 52 weeks. And as you can see, it not only affected actual production of chips, but areas of the supply chain like packaging and distribution. So now we're going to zoom back in on the automotive industry and take a look at what this looked like from their perspective. So in March 2020, that is right around when the government lockdowns really started to take off. Demand dropped for new cars, trucks, and SUVs. To react to this, automotive plants and their suppliers shut down. This was partly a reaction to the demand, partly also to protect their workers from infection. And then automotive companies also began canceling many of their orders. So, part of the business culture of the automotive companies is to practice just in time delivery, meaning they keep a tight rein on spending and hold minimal amounts of inventory, and instead rely on deliveries to be made right when parts are needed at the plant. So, since they weren't going to be making anything for a while for the foreseeable future, they canceled many of the orders they had pending, including those for parts that contained microchips. Now, as this was happening in the automotive industry, demand began to surge for consumer electronics, servers, wired and wireless communication, etc., for the reasons that we talked about previously, for everyone switching, working from home, going to school at home. Because of that, chip fabricators naturally reallocated their capacity to focus on these other businesses since their previous orders had been canceled with the automotive industries. And as a bonus for the chip fabricators, these new contracts were higher margin than the automotive contracts. Skipping ahead a few months to the summer of 2020, demand for cars, trucks, and SUVs returned much sooner than expected. Automotive plants reopened, their orders were reissued, but chip fabricators could not immediately react to these new requirements. For one, since they had switched their focus to these other applications, they had not been building up a stockpile of parts to be able to send to automotive companies. That being said, since new orders are being issued from the automotive companies, even the simplest chips were taking 10 to 12 weeks from start to finish to be manufactured. And chip companies were reluctant to switch their capacity from these newer contracts back to automotive because automotive didn't hold as high of a place in consumption, and so their buying power wasn't as high, and there wasn't as much incentive to switch over from what they were doing. So chip manufacturers did their best to add automotive demands back into what they were already working on. And now, skipping ahead today, what does it look like now? So automotive companies have been coping with the chip shortage in a number of ways. They've been building vehicles without certain chip components and with the intent to install them later, reducing complexity, R&D into part improvements to reduce the number of chips required, greater communication with suppliers and forecasting, placing orders earlier, partnering with semiconductor suppliers. Um, and as you can see over from the right, they are hoping to recover their global sales in the next couple of years. However, the chip shortage is still continuing for everyone across every industry. Uh, Places are working to open new chip manufacturing sites, but each site takes billions of dollars and several years to get up and running to full capacity. There have been COVID outbreaks in areas where chips are currently being produced, packaged, and distributed, which has disrupted the process. Different distributions to global shipping. People have talked about ports being backed up and things like that. There's also been acts of nature, disasters at plants that just can't be foreseen and can't be planned around, and different geopolitical issues such as the war in Ukraine, which is disrupting the supply of neon, which is one of the elements critical to semiconductor production. Ukraine produces about 60%, so that is also having an impact. So, um, where does that leave us? Unfortunately, that means higher prices and longer waits will continue for consumers. But as businesses find new and better ways to handle the shortages, hopefully those improvements will show some noticeable results for the rest of us. Thank you.
All right. Thank you very much, Helen, for the wonderful presentation. So we have a few questions for you from the audience. So the first question I have for you is that is it possible to control more functionality, maybe from a lower number of chips, but making those chips more powerful with the increased technology? Would that have helped the shortage problem?
It could. That is one of the things that automotive companies are working on right now, researching and developing the current designs that they have for parts. A lot of the parts that they make, I mentioned, contain these lower tech legacy chips, and there are so many of them. And because they had a system that was working and they were doing well with manufacturing, there wasn't necessarily as much incentive to prioritize researching how to consolidate those functions into a lesser number of chips. But that is something that is being pursued now. So I think that is something that will end up making a difference. But it does take time to do those things. So it's hard to say how soon will they would be able to see those results.
Interesting. So I have one more question for you. So there are certain trends in automotive industry going on right now, such as electrification or autonomous driving. So these kinds of trends generally require additional complexity on these parts or higher technology, which might require more chips or different types of chips. So how would you comment that these trends kind of interacted with the ongoing chip shortage problem?
I certainly don't think it's going to help. These new trends definitely require more parts containing microchips and increasing the technology and capabilities of the parts that they already are using. I think that in terms of autonomous driving, there's still a lot of research and development required before we're actually going to see a lot of them on the roads. So I don't think, I'm hoping anyway, that the chip shortage would be over by the time we would start seeing more of those on the road. Many experts are expecting the chip shortage to hopefully end 2023, maybe by 2025. Um, and in terms of EV, a lot of that's happening right now anyway. And although uh, more and more parts would require chips for those types of vehicles, because those are a higher complexity part, that's something the chip fabricators are currently investing more money in anyway. Hopefully, that would be more in line with what they're working on, and automotive companies would have more success in obtaining those types of parts.
I see. Thank you very much, Helen. So I have one more question for you, and this will be our last question. So this chip shortage problem is very topical, and it is very recent, and it caused a huge problem. So beyond this semiconductor problem that is being faced right now, has there been any other similar disruptions in the automotive industry that automotive companies can take lessons from?
I'm sure that there have been. The chip shortage is the one that I have been most involved with, but in general, I know during the pandemic, because of the reduced capacity of a lot of suppliers and plants for the automotive companies shutting down, disruptions in mail service, different types of global distribution that affected the availability of parts in general, not just the chip parts.
All right, we are thanking our first speaker, Helen Crimmins, and then going on to our next presenter. So our second speaker today is Chris Jobse, who is the CEO, founder, and co-owner of PIMvendors.com. With his knowledge of the product information management market, or PIM market, Chris is an important link between the retailer and the PIM supplier. As a senior master data and product information expert, Chris is advising customers to organize their data in the most efficient way to serve their omnichannel goals. So today, Chris will give us a brief history lesson on product data management and teach us how smart architecture and intelligent tooling can help. Chris?
Okay. Well, the story of product content management starts off in the days that a store owner is a local guy. He knows the customer, he knows the needs of the customer, and he can advise his customer because he knows the products he's selling. If his customer has a new demand, he just orders these products with his supplier. Things change when the owner starts to have more than one store, ending up in complete chain of stores like Woolworths or Sears. There are more employees involved in the relation with the customer, and they need to be maintained. The relation needs to be maintained in different ways. How does the store owner reaches his customers with the right information? Companies started to use advertisement in newspapers and started to publish product catalogs. A big example is Sears. They can be considered the masters of the catalog. To produce a catalog took a long time, gathering all product information, images, prices, sending it to a publisher, and in the end, distributing the catalog to the customer. To get the products in the store, a complex supply chain was needed. This could be managed via an enterprise resource planning system, ERP. Good, reliable product information is crucial for a smooth process. The ERP system was primarily meant to keep price, stock, and logistical information. It was not suited very well to keep additional marketing product information. This was then managed outside the ERP. This information was disconnected from each other. As there was basically only the catalog to be served with information, this was not a very big issue. In the 90s, e-commerce emerged. This was a game changer in getting correct product data to the customer fast and correct. The demand for information with the customer grew. The pace of the information flow increased dramatically. A lot of product information needed to be available because the customer didn't have the possibility to view and touch the physical product. So images, videos, manuals, etc. needed to find a location in the organization to be stored and retrieved. The information needed could not be stored entirely in the current systems like the ERP. Spreadsheets for product data and file system for product images were used to store product information. Many stakeholders became involved in managing this huge information pile, and the process started to be uncontrollable. To be able to manage the growing product information demands and to manage the time people needed to organize this process, a centralized repository needed to be created. This is called a product information management system, shortly called PIM. It replaces the spreadsheet jungle. More work could be done with fewer errors and fewer people. Now I come to the point of architecture. How do all these touch points interact with each other? What is the logical sequence? And how do I avoid redundant steps in the process? From a historical point of view, the process looked like this. A product was created in the ERP manually or automated. From the ERP, the product is added to the PIM. In the next stage, the supplier adds additional information to the PIM, or it could be provided by specialized data pools. The PIM serves all possible output channels like the catalog, the web shop, marketplaces, and more also social media channels. A more modern approach is positioning the PIM of the ERP behind the PIM. With this, the process of providing product data can be even more efficient. It doesn't need additional interaction with your suppliers as in a traditional setup. Data can be delivered in one go. Instead of producing product data yourself, suppliers and data pools will deliver product data. The PIM contains all information needed by the several output channels. It is considered the single version of the truth, the system of record where the whole organization can rely on. The ERP, in this case, is just another output channel. This approach has more advantages, especially when a long-tail strategy is used. It makes sense that not all product information ends up in an ERP, again, saving the organization a lot of work. So, by applying a smart architectural setup, you are able to maintain more product data with fewer staff. Thank you.
Thank you very much, Chris. That was a wonderful presentation. So we have some questions for you from the audience. How does good product data alleviate shortages on the supply chain?
Well, when you have good product data, you will have less failure in getting the right information and the right products in the right place. It's all, for instance, in automotive, when you have spare parts, you need to know which spare parts fits in which vehicle, for instance. And there are a PIM system is able to make relations between objects, and that makes it possible to have the right information for you in the end.
I see. Thanks, Chris. So another question we have is that, is there a shortage of product data, or is the bottleneck really in moving that data between silos from different players within the supply chain?
Yeah, as you heard, there is no shortage of data. There is a lot of data, and this data need to be organized in a proper way. And there is actually a shortage of people, and a shortage of people managing this data. And you want to have a lot of data because there is a lot of information, but you need to have smart people to organize this and smart systems to be able to organize this.
I see. So what you have presented on enterprise resource planning then, or ERP, so does ERP really address more of the people, like human resources side of this shortage question, or more on the product shortage question?
The ERP is an environment where you it's more about the logistical part of the organization. It's more of the finance part of the organization, and a PIM is more of the content part of the organization. So there are two different systems, which I always say they are married to each other. They need each other, and they can't do without each other. And HR is a different part. It's not really ERP. I think you have other ways of managing this.
Thank you very much, Chris. So our final speaker today is Dr. Ece Sanci. Ece is an assistant professor at the University of Bath School of Management. Ece received her PhD in Industrial and Operations Engineering from University of Michigan in 2019, and her research focuses on decision making under uncertainty with applications in disaster relief and disruption risk mitigation. So today, Ece will share a case study she conducted at the Ford Motor Company as part of her PhD work on supply disruption risk mitigation. So Ece, what are we going to learn from you today?
Yeah, so hello everyone. My name is Ece Sanci, and today I would like to present this study on mitigation strategies against supply disruption risk. Like Ahmet briefly mentioned, this is based on a research project that I was involved in during the last year of my PhD at the University of Michigan. So this was back in 2019. And so we were collaborating with Ford. So this is my outline for today. So first, I would like to start with a brief description of the problem environment we considered in the study. but I would like to spend most of my time on describing the framework we developed to choose optimal mitigation strategies against supply disruption risk. And finally, I will end my talk with some conclusions we derived from a case study at Ford. Okay, so this problem of selecting mitigation strategies against supply disruption risk, so this problem is especially important in just-in-time environment. And like Helen mentioned, just-in-time is the dominant management philosophy in the automotive industry. So the fundamental idea behind just-in-time is to keep inventory levels to a bare minimum, because this has certain advantages, such as it helps reduce inventory costs, improve production efficiency, and identify quality problems quickly. But implementation of just-in-time is only possible through very flexible suppliers which can promptly respond to the changing needs of just-in-time companies. So this is why typically just-in-time companies develop very close relationships with their suppliers. So single sourcing is quite common among just-in-time companies because single sourcing enables them to fully coordinate the deliveries with their own production schedule. But low inventory levels coupled with single sourcing increases the exposure to supply disruption risk. So in this study, we developed a decision support framework to choose the best mitigation strategy against supply disruption risk by considering these companies operating with a low inventory level and a small supplier base. So here we considered specific characteristics of a car company. Like, for example, a car company typically has its own tooling used by its suppliers, and typically this tooling level determines the capacity reserved from a supplier. So this is why, like, the first mitigation strategy we consider is to reserve backup capacity at the primary supplier through investing in acquiring additional tooling. Here, the second one, okay, I said single sourcing is the dominant strategy, but it is still an option to use dual sourcing. So the company can reserve capacity from the primary and secondary suppliers together, but this means a company will commit itself to source parts from these two suppliers regularly during business as usual periods. And if the secondary supplier is significantly more expensive, then this can create a major cost burden. And so the compromise here is to pre-qualify the secondary supplier and only use this supplier during disruption periods. And finally, here, again, I mentioned that these companies prefer to have very low inventory levels, but they can actually build up backup inventory using the time available before the launch of a new model or new program. And so typically, this is not very long time. Like, for example, in the case study we assume this is 8 weeks. So they can actually keep up to 8 weeks of inventory and use this backup inventory during disruption periods. So the building block of our framework is a multi-stage stochastic programming model. So this is a type of optimization model we use in operations research. So we use this model to determine the optimal mitigation strategy for a given time to recover and disruption probability parameters. And here you may say, okay, but these are very difficult to estimate. Like it's very difficult to come up with a point estimate for time to recover and disruption probability. This is why we use these strategy graphs. So first, we take the input from decision makers, like what are the ranges of time to recover and disruption probability they are interested in. Like, for example, in the strategy graph, we have time to recover from 2 weeks to 20 weeks and disruption probability from 0% to 10%. And we solve our model for each one of these combinations and then depict the optimal strategy on this graph. So if you look at this graph, like if we just focus on this 0% region, so this means basically there is no disruption risk. So only under this condition, only using like 100% regular capacity from the primary supplier and do nothing else is the optimal approach here. But as soon as disruption probability is something more than 0%, then we have to use a mitigation strategy. Like for example, here, if the time to recover is less than or equal to 8 weeks, then it's optimal to use inventory mitigation. If it is something between 8 weeks and 16 weeks, then we see a hybrid strategy here. So we integrate inventory mitigation with 50% backup capacity from the primary supplier. And if time to recover is more than 16 weeks, then depending on the disruption probability, it's optimal to integrate inventory with pre-qualification or integrate inventory with 100% backup capacity from the primary supplier. So the nice thing about using a strategy graph, it eliminates the need to estimate these parameters with high precision. Like, for example, if decision makers agree that time to recover is strictly less than or equal to 8 weeks, but they cannot really decide on the disruption probability. So regardless of the disruption probability, inventory mitigation is the optimal one here. So this can be a problem when deciding between these two strategies, but our results from our case study show that the regret of using a neighbor strategy because of an imprecise estimation tends to be very small. So this is why this in a way removes the burden of having very high precision estimations. Okay, so finally, I would like to show you these heat maps to understand the effect of these strategies on the cost. So this first heat map I have here, so this shows the expected total cost when we don't consider any disruption risk and determine the optimal strategy based on this. So in a way here, we just reserve 100% regular capacity from the primary supplier and do nothing else, like no backup capacity and no secondary supplier and no inventory, nothing else. So here for the 0% disruption probability, this one actually stands for this original cost. So this will be our reference cost because I cannot really reveal cost information here. But I want to show you here, like if there is actually disruption risk, like when disruption probability is 10% and time to recover is 20 weeks, the cost is increasing dramatically. In fact, here it is 3.55 times of the reference cost. But instead, if we use the optimal strategies shown on the strategy graph, like generated by our framework, this cost increases at most 5%. So to conclude, like from this case study, we observe that only relying on the regular capacity of the primary supplier can increase the expected total cost drastically when actually there is a supply disruption risk. But for smaller values of time to recover, just holding backup inventory itself is an effective strategy. For larger values of time to recover, it is more appealing to integrate backup inventory with either backup capacity or with pre-qualification. And finally, hybrid strategies are actually quite robust for all combinations of time to recover and disruption probability. And this actually removes the burden of estimating these values precisely. So thank you for listening to me. So one final slide I want to show you. So this is the second one here is actually our paper. This was published last year. But if you're interested in knowing like Ford's approach in risk mitigation against supply disruption risk, so there's this other earlier work by Sanci et al. So they first they have a framework to identify critical parts, and this actually becomes an input for our paper, because in our paper we don't really identify critical parts. We assume it is given to us. Yeah, thank you so much.
All right, Ece, thank you very much. That was very interesting. So let me actually directly follow up with the papers that you have shown. So you actually have two aspects to this study, right? First, you use the previous method in literature to identify which parts are the highest risk. Then you use your method that you developed on what is the best individualized risk mitigation strategy that you can use for that, for each and every part, right?
Correct. So, I would like to draw your attention. So this paper, the earlier paper, was actually published in 2015, and when we started this project in 2018, Ford already had this like very detailed study. Like they actually showed us like how they grouped parts into like different categories, and they showed us, okay, we identified this group as our critical parts. Like we want to use these mitigation strategies, especially for these parts. And in our framework, we assumed like we consider only one critical part. So in a way, you have to generate the strategy graph for each one of these critical parts identified.
Okay. So Ece, while the results seem very impressive from your study combined with both of these work basically, so I'm actually curious that how available, like what kind of input actually went into these models, and was that data already available? Was it usable, or did you just cherry pick certain parameters maybe, and then they were difficult to collect? So basically, how applicable is this model that you brought to a practical case?
Yeah, so along with these identified critical parts, Ford also provided us with some market analysis conducted by their purchase experts. So for example, tooling cost and unit production cost. So these are like the costs provided by the potential suppliers. So these were like critical, like important inputs into our framework. Our model needed these cost figures. Also, although we didn't really incorporate the uncertainty in demand, they told us, okay, we just want to consider like a constant demand, and this is like the demand value you can use. So again, demand for parts is another important input we use. But then there are some other parameters we couldn't get from Ford, because like some of the things are actually new, like they were not in practice. So for example, let's say pre-qualification of a secondary supplier. So in that strategy, we assumed like, okay, like you don't want to commit to this supplier, you just want to pre-qualify them. So this is something Ford didn't do beforehand. So for example, like how much it's going to cost to pre-qualify, like what is the upfront investment needed there? Or we assumed, for example, this pre-qualified supplier cannot immediately continue production, like right after the disruption. So there need to be some preparation time. So again, like what is this time? Like these are all unknown, because Ford didn't use this strategy before. So we, in a way, we came up with some numbers, but then we conducted sensitivity analysis. Like if our estimation is actually wrong, like if, like for example, we assume pre-qualified supplier will be ready in 6 weeks, but then we did analysis like, okay, what happens if something much less or much higher than 6 weeks? So this is how we considered all the inputs in the model.
All right, thanks, Ece. So I have one more question for you. So you have actually conducted this study before the whole pandemic and chip shortage crisis, right? So you have actually developed a model in a pre-pandemic world. So I'm just curious if there will be any other type of major causes that this mitigation strategy or this model that you have used would not be able to capture. For instance, like would it be able to capture whatever is happening right now, or if it cannot capture, let's say, then would you be able to adapt the model you have on the current problems we have?
Yeah, that's a very good question. Actually, it's one of the limitations of our paper, because like we started this project before the pandemic, so we started in 2018 actually. So back in that time, we only considered like this very extreme disruptions. that like for example, one of our assumptions, it was there's only one such disruption during the entire life of the program, which is typically like 3 years. So we assume like there's going to be only like one major disruption during that 3-year period. Of course, pandemic changed this, like, like after the pandemic, we are observing like there are multiple disruptions following one another. Also, like we assumed another strong assumptions in our paper. We assumed only like one supplier, like our primary supplier, will be affected from this disruption, because in the literature it is very typical to assume like one reliable supplier but expensive, and less reliable, like unreliable supplier but cheaper. So we were following that common assumption in the literature back in that time. But of course, again, after the pandemic, we see like multiple companies in same sectors or even multiple sectors can be affected from same sort of disruptions. So these are limiting, and definitely like we are looking for ways like how to adapt this into our framework and how to improve our model to also incorporate this new world, after the pandemic.
All right, thank you very much, Ece, for the wonderful presentation and the insights. So I think with that we can wrap up. Thank you very much to all our panelists and everyone in attendance today. We would love to hear your feedback on the event and hear what you'd like to see in the next upcoming Insightinars. So thank you all for attending. Goodbye.